It would be nice to have it just because we might convert some objects into cats or operators just because these are objects that folks are more familiar with. So it would be nice to see the conversion back to a standard object. Okay, well, it's a few minutes past 7:30, so why don't we start? So the last, pretty much the entirety of today was focused on state vector simulation. This is the most general way to represent quantum state. It's in many ways the most fundamental one. It's the exponentially expensive one, and that exponential expense is frequently kind of the intuition behind why do we expect that quantum computers might be useful, because quantum computers don't pay exponential resources to simulate these, to run the dynamics that on a classical computer we represent by exponentially large state vectors. However, there are many simulation techniques for quantum systems that are not exponentially expensive. They're not general, but they're very useful nonetheless, and applicable to a vast array of important types of dynamics. They're techniques that are specific to a type of dynamics, where you restrict what the dynamics of the system are permitted to be. The prototypical examples are Gaussian quantum optics, which deals with multi-mode, arbitrarily squeezed states. So with these, we can call them semi-classical states to an extent. And it's really useful when studying interesting sensors built on pretty standard laser technology by today. Then there is another big class, the class that we'll be discussing today, of Clifford circuits. These are focused on dynamics of qubits, but qubits that are in a state that's an eigenstate of a Pauli observable. These are extremely useful, especially when we're describing error correcting codes, error detection techniques, anything that can be expressed in terms of bit flips and phase flips of your qubits. And if you're going to ever work on anything related to error correcting codes for qubit systems, this is one of the most important techniques that you need to know. Depending on how much time we have today, we might actually get into the discussion of error correcting codes. But for the moment, let's focus more on the modeling technique that can be used down the line, maybe for error correcting code work. Of note, there is also other style of techniques that you can use for representing restricted dynamics, where you don't really restrict yourself a priori to a type of dynamics, like with Gaussian quantum optics or with Clifford circuits. Rather, you do some something not too different from principal component analysis, from finding the most important basis vectors for your state, and then working in that very special basis. Those are much more general methods, but they're also kind of in between in terms of expense. They're not as easy and fast to implement compared to, say, Clifford circuits, but they would be applicable to much more arbitrary type of dynamics. That's the tensor networks approach, and that will be covered tomorrow. Okay, so with that, let's focus specifically on the Clifford circuits. As I mentioned, important for anything that might be related to quantum error correction or entanglement distribution, or many topics related to quantum networking. In terms of tooling that you might use to work in that direction, you might be interested in looking into STIM. It's a C++ library with a Python wrapper. And if you're going to simulate large error correcting codes, it's probably one of the most important tools to get familiar with. But on the other hand, if you want to work with the linear algebra of these states, it's not as expressive. Similar to how I was distinguishing earlier today, quantum circuit simulators, quantum computing simulators, from more general purpose tools for arbitrary quantum state dynamics. In Julia, we'll be using a tool that's developed as part of the work done under the Center for Quantum Networks. Again, the funding source for the summer school, we'll be using QuantumClifford. The advantage of this tool is that, well, it's implemented in a single language. So if we're going to look at how to implement something that's fast, and that's kind of the point of the session today, to understand behind the scenes how this formalism works, it's much easier to use it from a single language because we won't need to jump between Python and C++. And C++ is not as easy to read anyway. And the other advantage is that, again, it's a tool that makes the linear algebra properties of the objects that we'll be working with much more obvious. It's not something that's specifically extremely highly optimized and fine-tuned for circuit simulations, although it's fairly optimized. But more importantly, it provides you access to all the interesting mathematics behind these data structures. Then if you want to work with Clifford circuits that have some small amount of non-Clifford circuits in them, we'll discuss that as well. Tools that you might want to use are QuantumClifford has support for that. And in Python, tsim out of Quora Computing and Clift out of the Unitary Foundation. Okay, so with that out of the way, let's start talking about this formalism, this Clifford circuit formalism. So I guess first thing, just so that I can orient myself, how many of you have worked with that formalism before in some sense, in some setting? Okay, not that many. So I'll go through describing how you represent a state, how you represent the dynamics of a state. We'll derive how some of these update rules and actions of an operator on a state are implemented. And we'll focus really more on how do you program such a simulator. And depending on how quickly we're done, we might do some simulation of error correcting codes as well at the end. Okay, so first thing, in a Clifford simulator, in a Clifford toolkit, one of the main things would be to figure out how to represent Pauli operators. So there is a shorthand syntax for this in QuantumClifford, and there will be an equivalent shorthand syntax really in any comparable tool. You write a custom string where before the string you use this large P to denote that this string should be immediately interpreted as something more than just a string, should be turned into some other object. And let's write down the single qubit Pauli operator Z. One thing that I might want to do from time to time here is to convert these data structures into the exponentially expensive structures from a state vector simulator. I'll be doing this every so often, just so that you can get a sense of semantically what these structures represent. My assumption here is that if we look at how these things are implemented in terms of a state vector simulator, you have more intuition in that context. So let's convert this into an operator. So this object is coming from QuantumClifford, while this constructor is coming from quantum optics. And this symbol here is just a bar and a bigger than sign. It's just a convenient way in a number of different languages to pipe operations together. It means take this and put it as an argument of this object. It's basically just a syntactic structure for for this. This notation here and this notation here are the same thing. This turns into a triangle just because I have some fancy font for my editor that automatically turns symbols that are next to each other into ligatures. If you're a typography geek, you might have seen how, especially in French, things like T, one after the other gets a single bar. It's cutesy font rendering technology meant to make text more pleasant to read, and programmers have co-opted it to introduce fancy mathematical characters that just pop out from their source code. I'm just giving this intro to avoid any confusion. This is nothing more than a bar and a bigger than sign, and it's just a syntactic sugar for piping, for putting this thing as an argument of the next thing. It's just that we'll be doing a lot of write some object and maybe after that convert it. So in terms of writing, this makes it a little bit simpler. So let's first run this guy on its own, just pz. And it prints out as plus z, nothing too interesting here. It has some printing method that makes it more legible. Now let's do the same thing, but pipe it through operator. And it prints out as unitary operator, as a diagonal matrix with a diagonal of 1 and -1. Let's do a couple more just to get familiar with the notation. Poly x. When I print it out, it's if I convert it into a unitary matrix, it's a unitary matrix with an off-diagonal 1, 1. More importantly, I can have a polystring of multiple qubits. And this gives me the tensor product of poly x and poly y. Basically, if I write this guy, is it equal to the tensor product of x and y? And this better evaluate to true. It did evaluate to true. So I guess my first question is, what will happen if I run this command? So how many qubits are here? I don't know, more than 20, I think. What would happen on this computer, on this 6-year-old laptop, 7-year-old laptop?
Run out of memory.
Yeah. This is converting it to an operator, even as a sparse matrix. This would require 2 to the, I don't know, 20-ish bits. It will crash with a memory error. I'm kind of enticed to see how stable my machine is. Okay, we might really regret that. If the recording on Zoom cuts off, you would know why. It's doing something. The recording is still up. Okay, anyway, while this is hopefully crashing, obviously I can create the P object, that string. There is no problem in creating that string. The problem is in converting it to a unitary matrix. Okay, it crashed in a reasonable manner. It didn't crash Zoom together with it. My browser is still up. Okay, good job. So let's do the same thing again, but I'll delete the conversion to operator. And let's discuss the data structure used to represent this P. Still loading. I'll put it in a variable named, let's call it small p. Yeah, this, as I mentioned, 7-year-old laptop, it's not very happy when it's screen sharing and running compilation at the same time. But anyway, it had no problem with this. And if I run it a second time now that everything is loaded, it should be instant. Yeah. So let's look into this object P. And depending on the language you're working with, the conventions of how to use structures might be different. But in Julia, generally, you're not expected to look inside of a structure, to do p dot and look at its fields. You can, of course, do that when you're working on something. But to make code be extendable through multiple dispatch, you probably would want to define an API. So what I'm doing right now is not how you would use the library, but how you might learn about the internals of the library so that you contribute to it, or just learn how something like this is implemented. That's similar to how someone should think of C and C++ and Rust. It's very much unlike how people think of Python. The object dot something is part of the public API. Anyway, if I do this and press tab twice, I see that there's a couple of fields for this structure. There's n-qubits, phase, and xz. And I want to look at this xz object. This xz object is some vector of UN64. It doesn't look very legible, so I'll rework it a little bit to make it slightly more legible. Hopefully that will start giving you some ideas of how is this object implemented. So first thing, let's start with a smaller polystring, just so it's a little bit more legible. And let's look at its xz field, the actual thing that is stored in the computer to represent the structure. Again, not super readable because this is printed in hexadecimal. It's two numbers printed in hexadecimal. But I can print them as binary strings. Julia has a couple of nice tools for converting from one basis to another. So I'll just do that so that we can start figuring out what's inside of this object. Another thing I'll do is that, notice that this is uint64, an unsigned integer of 64 bits. And most of those bits seem to be zeros. So I'll focus only on the last few bits. I don't want to bother my display with all these zeros. So first thing I will do is I would convert these guys to smaller integers, basically discarding all of the zeros in front. Okay, this is much more legible. And then, more importantly, I will convert this. I'll convert these integers to bit strings, so they're printed out as bits, not as hexadecimal, which is much more difficult to read. So let's see. X, Y, Z is stored as two integers whose bits read 0, 1, 1. And the other integer reads 1, 1, 0. I'll just copy this here to share it with the live share. live.QNumerics.org should be sharing this. So why don't you guys play with the conversion from this nice user-facing syntax into this backend binary representation and try on your own, maybe not on your own, with your neighbor. With your neighbor, please try to back engineer how is this storage actually working. Let's spend 5 minutes with your neighbors. Please talk to your neighbors over that and try to reverse engineer this storage format. How is this string actually stored in memory in terms of bits? All of this boilerplate around it is to extract the bits and to print them in a pretty fashion. And if the setup or my question didn't really make sense, please speak up. Making sure that we all have good momentum at the start will be important for your comfort throughout the next 2 hours. So please let me know if my question didn't make sense. Yeah. So all that this boilerplate is doing is printing for you the binary representation of this object I wrote. P, and then the string X, Y, Y, Z is just a pleasant syntactic sugar for representing some object in memory. The same way that sigma m on a basis object was a convenient syntactic sugar for some unitary matrix. We are not using unitary matrices here. If we were using unitary matrices, we saw that it would just crash my machine. So we're using some different data structure to represent the Pauli operator x, y, y, z. This data structure, the binary representation for the actual bits behind this data structure, is these two bit strings. All of this boilerplate is just to extract and print the bit strings in an easy to read manner. So my question is, forget about the boilerplate I'm using to extract the bits. What is the meaning of these bits we're storing? And a way to reverse engineer that is to try to write different Pauli operators and to see what they're represented as. And what's the rule for this representation? .xz is where this data structure actually stores all the data. Yeah, it's I decided to name that part of the data structure this. The location where the actual interesting data is stored is in .xz. I'm just converting this to a smaller unsigned integers to throw away some unused data, and I'm converting these integers then to bit strings so that they can be read as a pleasant to read string for a human.
So it's actually something like this. It's doing the routing
What was the question? Up to a phase, z is equal to y.
It was either be applying identities, yeah.
So what?
So can I do I?
So then I will have, you should get the same result.
The z will go.
This will change.
Yeah. So
does this kind of in some way give you some weight of the
and then phase. Oh my God.
It's going
So any guesses?
for
It has a name for X, Y, and Z. So X is a 1 when you hit the first, and it just the bit shifts over lines it up. So you just look at the right hand side, read across like at the end.
Yep, that's pretty much it. I'll just repeat so that everyone can be on the same page. X is stored as true, false, a true in the first byte, and a false in the second byte. Z is stored as false, true, a false in the first byte, and true in the second byte. And Y is stored as true, true. Both the top and the bottom will have a true. So let's see this in action here. Look at the X. The X is something that I said would be true, false. True, false. The Y would be something that's true, true. True, true. And the Z is something that's false, true. So why bother with this potentially convoluted way to represent it? Well, how much data, how many complex numbers do you need to represent a Pauli operator on 8 qubits if you're working in your typical representation, in your state vector representation? For 8 qubits, we need 2 to the 8 by 2 to the 8 matrix, right? Am I missing something here? It's that many complex numbers. We need that many, not bytes. A complex number is a bunch of bytes for the real floating point part and a bunch of bytes for the complex floating point part. So this will be this much, and then to turn it into bytes, twice 2, because we need the real and complex. And then each real and each complex part is itself, 16 bytes for float 64. So we need that many bytes to store an 8-qubit polymatrix. That's a lot of bytes. That's 2 megabytes. While in this representation, P, X, Y, Z, Y, this is 4 polys, Y, Y, Z, Z, this is 8 polys. This guy oops, it's not ZX, it's XZ. This guy is 2 bytes. So instead of 2 megabytes, we need just 2 bytes to store this object. I mean, at the end, it's not too surprising. We can write down a poly as just the product of an alphabet that has only 4 letters. So it's not surprising that we can pack it pretty nicely and neatly. The question is, in this representation, can we do anything more than write down a poly? For instance, can we apply a poly to a state? Can we take the sum of 2 polys? Can we take the product of 2 polys, the tensor product of 2 polys, the commutator of 2 polys? Some of these things we can do, some of them we cannot. We cannot take the sum of 2 polys represent this format because the sum of 2 polys is not a poly anymore. But if we're working only within the group of polys, if we're working only with operations that map a poly operation to a poly operation, this representation is exponentially better. We need not 2 bytes, we need 2 bits to represent an arbitrary single qubit poly operation. Of note here, you will notice that I'm not writing stuff like true, which is, if I write this true here takes a whole byte, and this true here takes a whole byte. This object takes 2 bytes. That's a very wasteful way to store Boolean information. Instead, you might have noticed this .xz object is not an array of Booleans. Rather, it's an array of unsigned integers, and every single bit of the unsigned integer is interpreted as a Boolean of its own. This type of packing, where in a single byte you pack 8 bits and you work with a single byte, you think of the single byte as a list of 8 Booleans, this is a very frequently used abstraction that increases the performance of your code drastically. Because say you want to do a logical operation between 2 Booleans. If you're going to do that element-wise between vectors, well, if you have 10 Booleans stored as bytes, you would naively need to do 10 CPU operations to get the element-wise operation between those 2 vectors of Booleans. For each Boolean, you will need to execute an operation. But if you pack them in this fashion, you can do bit logic, where at the same time you act on all of the bits of your byte with a single CPU instruction. So this is a very, very low-level parallelism that gives you a speed-up factor of 64 before you even care about some high-performance vectorized extensions to your CPU. I am kind of going in the weeds here, but I just wanted to mention that if you see something like that, know of it as a fairly common optimization trick where you don't store Booleans as a byte after byte after byte, but you store multiple Booleans in a single byte as the bits of that byte. That might make the code a little bit more annoying to write if you don't have good abstractions, but you can always create some structure like here that packages all of this annoying bit logic for you. And if you like this type of puzzles, there's a whole set of internet wikis with trickery of how you can implement weird algebraic operations directly in terms of bits. There's a whole subculture on the internet about writing fancy bit logic. Okay, we won't really need to be talking more about bit logic. Let's focus on what we can do with this object. Well, one thing, we can take the product of polys. So how does that work? Let's look again at, actually, I'll get a helper function for myself. I'll define this bits that takes an array and it prints the bit string for that array. And I'll be using this to simplify my work, the boilerplate for showing you how things are working. So let's do bits of px. Px, sorry, px dot xz. I do need to extract the array. Nothing too interesting here. Let's do the same for z. Nothing too surprising. And now let's do for the product of x and z. So I guess my question now is, how do you implement matrix multiplication in this data structure? Obviously, we don't have unitary matrices anymore. We won't be running actual matrix multiplication of complex matrices. We will be running something that's acting on the bit representation. And the nice thing is that if you look at this guy and this guy, the operation you need to do is just the element-wise logical AND. Let's do another example. Let's do z times z. Z times z should be identity. I defined it here. Yeah, it should have just popped up. Yeah, bitstring is in the base Julia library, and bits is something I just defined to simplify my work, and it should have popped up in live.qnumerics.org. So let's do z and z. So we took one true, we took another true, and what's the operation that from two truths is giving you a false? I think I misspoke. I might have said the logical AND. No, it's not logical AND. 1 and 1 is 1. It's the logical XOR, the exclusive OR. This is an operation that you will see very often in this type of Boolean algebra. Yeah.
So, when you multiplied x and z, your output has 1, 1.
Yeah.
We might interpret as y. But over here, your output is minus I times y. So where does the minus I come from in this representation?
So we don't have only xz, we also have phase. And there is some rule for counting the phase. It's slightly more complicated Boolean rule, but it's again just a formula for how you reduce the two vectors together, the two Boolean vectors together. Okay. So multiplication of poly strings in this data representation is turned into an XOR of Booleans. So that's the first step. If you want to implement extremely fast multiplication, what we need is a Boolean XOR operation. Instead of needing a floating point accelerator on our CPU, we just need the very basic arithmetic unit. Okay, so let's show this in action, actually. I want to make a large polystring. So this is the number billion. It has 9 zeros. And I will make a random poly operation. The left poly operation will be random poly a billion, and I will put a semicolon here so I don't try to print it out. It's a large string. And I'll make another one here. And this will be a random poly string of 1 billion qubits. And that was quick. It's done now. So how much space does this require? I mean, if it was stored as a unitary matrix, it would require more space than the universe. But here it just requires, well, let's see, billion times 2, because we need it for the x and for the z term, divided by 64, because that's how many bits we store in a word. The 64-bit object is frequently called a word on a modern CPU. So this is 3 times 10 to the 7 words. And let's do it divide by 8, so it's in terms of bytes. And divided by 1,000, so it's in terms of kilobytes, divided by 1,000,000, so it's in terms of megabytes. I just need to use only 250 megabytes of my RAM to store this object. But the fun part is let's do some operations on them. For instance, let's check whether they commute. We can check whether 2 billion qubit polystrings commute in the blink of an eye, literally. Let's time it. It took 50 milliseconds to work with a polystring of length billion qubits. That's the value that this data structure provides to you.
What was the outcome of your commutation?
Oh, yeah, good point. Com is a commutation check provided by this library. And X and Z don't commute. It gives you a 1 as a flag for commutation. But XX and ZZ do commute and gives you a 0. And it gives it to you in this format, 0 and 1, just because this is very convenient for more bit manipulation operations down the line. Because if you're adding up the phase, there's other bit operations to compute the phase. And that requires you to know whether they commute or not. Okay, questions up to here? Okay.
And now we have really confusion. Is the chance 50-50 or whatever commutation?
Well, let's see. X commutes with itself and I, and doesn't commute with the others. And that's the rule that you have for everyone else. And if you have 2 bit strings that commute or not commute, if you add an extra element to each string, whether their commutation relationship changes depends only on those 2 extra elements. And whether those 2 extra elements commute or not is a 50-50 thing. For a single qubit operation, it's easy to figure it out. For a single qubit operation, it's easy to see that it's 50-50. And given that for a multi-qubit operation, it depends only on the last qubit, basically. It is indeed 50-50 for sampling from the ensemble of billion qubit polys. Okay. Let's just a little bit more explicitly verify this rule I'm telling you about how the multiplication works. Let's just look at what am I doing here. I'm multiplying the poly objects and I'm extracting the binary data, and then I am printing it as bits. While here, I'm first extracting the binary data. I'm performing the element-wise XOR. This is just the Unicode sign for XOR. And I'm then printing the bits. Let's verify that these 2 things are equivalent. So this is the result in terms of binary representation if we do the multiplication in terms of poly representation and then extract the data. And here it's if we extract the data, manually do the XOR, and then print it out, is the same result. Not too surprising because internally, this multiplication operation is implemented exactly through this fashion. And really what I want to convey here is that you can do billion qubit operations in milliseconds. So this just lets us work with poly operations and products of poly operations, no sums of poly operations, nothing else about poly operations, not even applying a poly operation to a state. It's just products of polys. And when you notice that the multiplication table of poly operations is basically a logical XOR, or in other words, addition modulo 2, this kind of becomes obvious. There's not much excitement behind of this. After all, what can you do with just that? Nice thing is that you can actually do a lot when you start building on this. You can represent the dynamics of a lot of interesting states. So let's start focusing on that now. We'll be talking about states that can be represented as eigenstates of poly operators. Before we do that, any questions? Yep.
I just was messing around with the random poly. How efficient is it to create a random poly?
It's pretty ridiculously fast. It's nothing more than creating a sequence of random unsigned 64 integer words. And creating a random unsigned 64 integer word is something that your CPU probably can do in a single instruction if it has it built in. And a lot of them do have it built in. It's such a common thing necessary for encryption, for accessing any HTTPS web page, that it's a triviality. Okay, so I guess I have a question for you guys. Who remembers the distinction between Schrödinger picture and Heisenberg picture from their quantum 101 class? Okay, that's a good number. So I will talk a little bit about that distinction, but I'll frame it in a slightly different way. So one option is to represent your state in the Schrödinger picture as the state vector and to track the dynamics of that state vector. And to think of the state vector as something not too different from a classical probability distribution, but there's slightly different rule for external probabilities. There's this complex amplitudes. But the Schrödinger picture is nothing more than generalization of classical probability theory, where you have, instead of stochastic vectors representing probability distributions, you have kits representing, let's call it a quantum probability distribution. That's not a term of art, I'm just making it up. And then instead of in classical probability where you have stochastic matrices, which are the most general time evolution operation that can act on a probability distribution being a stochastic vector. Now you have unitary matrices, which are the most general operation that can map a valid quantum probability distribution to another valid quantum probability distribution. So if you're coming from classical probability, this is a very natural way to represent quantum dynamics. However, maybe you want to represent quantum dynamics in terms of observables, because as a physicist, you like thinking about observables, not about abstract probability distributions. We define observables in terms of operators, and now we can talk about a complete set of observables that defines one single possible state. Well, how do you use operators to define a state? Well, you talk about the eigenspaces of those operators. If you have enough operators such that their eigenspaces, the intersection of their eigenspaces is one-dimensional, now by enumerating those operators, you have a complete description of a specific state. And that's what we'll be doing here. Naively, it's kind of stupid because an operator is way more expensive than a vector. And it's not like I'm asking you to have one operator. I'm asking you to have enough operators such that their intersection of eigenspaces defines a single vector. It's one-dimensional. That sounds ridiculously expensive. There are situations in which on paper that's very pleasant to track because the algebra of operators might be more easy to track analytically. Or there are situations numerically where operators end up being extremely cheap to represent in the computer. Like here, a poly operator is extremely cheap, as we saw, to represent in this format. So as long as the states we want to represent are eigenstates of poly operators, by using the Heisenberg picture, we can use this data structure to represent states, not just operators. Okay, so let's talk about the space of the eigenspace of poly operators. Some nice thing about poly operators is that single qubit poly operators, what are their eigenvalues? I mean, for the Z operator, it's kind of obvious. It's 1 and -1. It's a diagonal operator. And for the X operator with eigenvalues with eigenstates plus and minus, it's also +1 and -1. For the Y operator as well, and the identity has very obvious eigenvalue, 1. So the eigenvalues of your poly operators are plus and -1. And the nice thing about plus and -1 is that products of plus and -1 is also just plus and -1. So the eigenvalues of any product of poly operators, no matter how many qubits you have, will be just plus and -1. And now you have an operator, a poly operator, that lives in an exponential large space, but it divides that space in two equally sized eigenspaces with eigenvalue +1 and eigenvalue -1. Well, if you have this space of size 2 to the n, and then you define one operator and you say that only eigenvectors with value +1 are vectors you care about, you just, by specifying that constraint, that your state has to be an eigenvector of that operator, you just divide your space in half. So instead of having 2 to the n possible options for what the state is, now you have 2 to the n -1. And if you continue doing that, if you define n poly operators of length n, you have fully defined a quantum state. And let's see that in action. I've been talking a lot without writing, and maybe for next time I should be writing on my screen. But let's look at this case. Px, no, actually, let's start with Pz. My first question is, what is the one single ket for which is an eigenket of z with an eigenvalue +1? It's 0. And I'll introduce slightly different data structure. If instead of P, I write capital S, this now represents the state stabilized. Stabilized is just a fancy word for it is an eigenstate of. So the state stabilized by operator Z, the state that is an eigenstate of value with eigenvalue +1 of the operator Z. So this object now, the state stabilized by this poly subgroup, this is my way to represent the state 0. Let's also convert it to a ket. So this guy is coming from quantum optics. This guy is coming from quantum Clifford. If we do this conversion, we see that it's a ket in the basis of spin 1/2 particles where all of the amplitude is in the first basis vector. Well, what would be this state? The one single ket which is stabilized by the poly operator X. If I just run this, it's the plus state. It's 0 plus 1 over square root of 2. The interesting thing happens when we start working with larger states. So let's do this guy. This guy on its own, well, we have one poly operator on 2 qubits. It doesn't fully specify my state. So I need to start adding more. So who is the unique ket which is stabilized by xi and ix? It's the tensor product of plus and plus. And let's discuss a few properties here. So first thing, notice that this guy requires a quadratic number of letters, while this guy requires an exponential number of complex numbers. This way of representing our state is much more efficient than this way of representing the state. For the moment, again, we have only state representation, but we'll start soon seeing also how we'll act with gates on these states. So we're just building up the algebra of capabilities. We know how to do the algebra with state vectors. Now I want to see how to do the same algebra, but with this binary representation. Yeah, it's just a shorthand notation for something that's stabilized by this Pauli operator and something that's stabilized by this Pauli operator. It has to be stabilized by both. It has to be a mutual eigenvector of both of them with eigenvalue +1.
Between them just by space?
Yeah. Or if you wanted to read a little bit prettier, maybe like that. Both of those work. This structure is frequently called a tableau, which is, I'm pretty sure it's just the French word for a table. And it's really just a matrix of the letters X, Y, and Z, and I. Yep.
I guess you said by default, it chooses the state that's stabilized by that operator with eigenvalue +1.
Mhm.
What if you wanted the one with -1?
You just change the sign of your Pauli operator. So let's see whether this works. What is the one and only ket which is stabilized, which is an eigenvector with an eigenvalue +1 for the Pauli operator -x? It's the minus state. Okay. Yep.
Could you explain again why xi alone wouldn't?
If I just write this guy, I have one Pauli operator, which will be divided, and one Pauli operator of 2 qubits. So what is the space on which that operator acts? It's a space of dimensionality 2 to the 2, 4. It's an operator that has 2 eigenvalues, so the dimensionality of the eigenspaces cannot be 1. The dimensionality of the eigenspaces, given that we know that they will be evenly split, will be 2. So a single operator defines a subspace, but it doesn't define a single ket. You want a one-dimensional eigenspace. And that's why you need multiple operators. What was this term that they drew in you in Quantum 101? Complete commuting set of observables, something like that? Well, this is not a complete set. Yep.
So in this state notation, if I do xi space ix,
this is just a shorthand notation for the tableau, the statement that you need to obey both of these constraints.
So interesting thing is in the second constraint ix, I can keep adding other Paulis like z, x, and it's still the same answer.
We'll get into that.
Oh.
Yeah.
And you got how many?
Well, for a Pauli operator, we'll be dividing the eigenspace, the whole space in 2. So if we have a space of dimensionality 2 to the n, we need n operators so that we divide it n times so that we are left with a dimension of 1.
The remaining thing is just identity and
Yeah.
else commutes with identity. So
Yeah.
Would XX be the same?
We'll get into that. But before we do that, I actually want to ask the following. So we have an operator xi and we have an operator zx. Both of those operators have, those are Pauli operators. They have eigenspaces. Both of those operators divide the Hilbert space of 2 qubits in half. Is there a well-defined ket that is an eigenket of both of those operators at the same time? I'm trying to allude to a theorem that you have definitely encountered in your linear algebra class when you were doing diagonalization of matrices. If for you to have a ket that is an eigenstate of two operators at the same time, they should be commuting, yes. And do these guys commute? Well, I and x commute, but z and x do not commute. So you cannot have an object that's an eigenstate of both of those operators at the same time. So this tableau, this stabilizer tableau, is a valid data structure properly representing a ket only when all of its rows commute. That's a defining property of a stabilizer tableau, a requirement for a stabilizer tableau to represent a state. If that's not the case, the data structure is inconsistent with itself.
Is this something that the S string function will check?
No.
Okay.
There are some other tools in here that will be doing that checking for you. And you can add validation. But for this particular API, for this particular constructor, it doesn't. Because there's some situation where on purpose you would want a more general form of a tableau, and we'll go into those as well. I mean, I hope that this will just give me an error. I don't know whether let's see what it's doing.
It gives minus at the end.
So how did it get this? As a homework assignment, do the following. Methods, ket. So you can see all of the methods that ket has. 6 different methods. Ket of not this guy, that's complicated. Ket not this guy, also complicated. Okay, ket of QuantumClifford.abstract stabilizer. So what is this doing? Let's open this piece of code. Stab to ket, let's find where this function is. Oh, this is fun. It's converting your stabilizer to a graph state. The graph state has easy conversion to a ket. It does that conversion, and then it applies all of the local operation that converts that graph state to well, to the correct local basis. And somewhere here, there's the implicit assumption that things are commuting. I don't know where. But this can be a fun place to add validation. This is, if you want this to be your first contribution to open source, this can be a very cute small project. Happy to help with it.
There or function or whatever is S.
S is just a constructor for the simple data structure. S doesn't do anything more than it reads the letter X and it stores the Booleans 1, 0. It reads the letter Z and it stores the Boolean 0, 1. It's just something that prepares it from a string into a list of bits. It's this function stab to ket that's called in order to convert the data structure into a ket, into an actual vector of amplitudes. You can totally look into the structure S stabilizer and potentially add validation to it, but validation can be expensive. So it's really a question of API design, whether you want validation or whether you want this to be a responsibility of the user. And it's a really difficult balance because a user that knows what they're doing, they might want to abuse this data structure to do something interesting with it. And we'll actually be doing that abuse in order to make the Clifford circuit simulator faster. We'll start by something called the stabilizer formalism. We're almost completely done with it. And when we're done with that, we'll introduce the destabilizer formalism because physicists are so good at naming things. Okay, let's go back to the main topic. Other questions? Yep.
So far we've only done like X, Y, Z. What about the other, like the Hadamard
We're only talking about Pauli operations. We're talking about states that are eigenstates of Pauli operations. We are explicitly incapable of representing states that are eigenstates of other unitaries. We'll be able to show that we can simulate some other unitaries, but so we're still stuck at the state representation. We haven't discussed dynamics yet. Other questions? Well, just one more thing before we start discussing dynamics then. One important way to think of this tableau is, and that's really the reason to represent as a matrix, is really thinking of it as a list of linear equations that your state needs to obey. Obviously, an equation about something being an eigenstate is not a linear equation. But when you represent it in binary, this constraint of being a mutual eigenstate turns into a system of binary linear equations, where addition is modulo 2 and multiplication is the AND operation. 1 and 1 is equal to 1, 0 and 1 is equal to 0, 0 and 0 is equal to 0. And that's very valuable because the vast majority of machinery you need to build this simulator now that works with stabilizer states is nothing more than linear algebra over the binary field. So wherever we had multiplication of large, exponentially large complex matrices, now we'll have multiplication of linearly large binary matrices. But again, we'll be restricted only to working with polystate, with eigenstates of Pauli operators. In that sense, you know how if you have a system of linear equations, a row operation doesn't change the solution. You can think of a matrix as a way to define a vector. The one single solution that that matrix has, when interpreted as a system of linear equations, defines a vector. Same thing here. The one single solution that this list of linear binary constraints has is our state. And a nice thing I want to mention is that we'll compare this guy and this guy. Are those two tableaux representing different states? Let's lazily check that. What is this kit? It's the tensor product of plus and plus. What is this kit? It's the tensor product of plus and plus. How come two different tableaux represent the same state? Well, if you have an eigenvector, that's an eigenvector of the operator A and B, it will be an with an eigenvalue plus 1. That eigenvector will be an eigenvector of the operator A times B as well. And all I did here was I multiplied this guy into this guy, and I put it in here. So if something is an eigenvector of this and this, it will be an eigenvector of this and the product of these two guys. And that's where this row operation independence comes in. So the same way two different matrices can represent the same solution, the same system equation with the same solution, two different Pauli operators, two different lists of Pauli operators can represent the same vector that is a mutual eigenvector with an eigenvalue plus 1 of all of them. And a quick question here. What is a standard way to canonicalize a matrix? To check whether two different systems of linear equations would have the same solution? How do you check that? Who knows what Gaussian elimination is? You know how you have some set of linear constraints and you kind of turn them into a canonical upper triangular form in which even if they were different to begin with, at the end they will look the same because you did all the raw operations that convert them into one canonical form. You have access to that here as well. So let's make some big random state. Random stabilizer of 50 qubits. So this would be 50 Pauli operators acting on 50 qubits, fully defining one specific state. I will definitely not try to do this because to again just crash the system with out of memory error. And I'll put this in my in a variable named s. Let's run this. It printed out. It's just some list of random Pauli strings guaranteed to commute. This is actually some interesting samplers to implement here. It's not obvious how do you implement a way to generate randomly 50 Pauli operators that actually commute with each other. If you just generate them independently, it would be exponentially unlikely that they all commute. So the theory of how you sample randomly from stabilizer states is fun. Anyway, it's implemented here in this function. And let's canonicalize this object. Actually, first, for a lot of these, there's a predefined plot recipe. So let's see whether I can get this to work. It's a bit more complicated than that. You can do that, but you cycle way too often. It's not easy to do that split if you're sampling randomly. So let's check this.
Quick question.
Yep.
That how am I supposed to read that string that it just generated? It's not on the same number of qubits, right? Each of them, or are there identities?
Are you talking about this one?
Yeah.
Underscore just corresponds to identity, and we have 50 columns, and we have 50 rows where some of the rows are skipped so it can be printed on the screen.
Oh, I see. Okay, so each row is a different.
Yeah, each row is a different operator. Just a second. And because I personally find this really difficult to read, I'll represent it graphically with this stabilizer plot. Let's see whether it works. Oops, what did I do? I think it's still loading the plotting library. I have on the side my CPU utilization is really unhappy that I'm streaming all of this right now. Okay. So what this will do is it will just represent the Tableau graphically, kind of like a heat map where each square of the heat map will correspond to a single qubit Pauli, and by color it would encode whether it's identity X, Y, or Z, and it's just easier to read than this. But I'm pretty confused why is it being so slow. Oh, finally. So you can see this color is Y, Z, and X, and you can see that this random stabilizer Tableau just looks messy and random. It's kind of cool that there's a trick to ensure that all 50 rows here commute, but that's really all of it. And I was mentioning that the whole point of the canonicalization operation would be to be able to say whether two tableaus represent the same state. There are a number of different canonicalization operations available in the literature. So let's just run one of the more standard ones. And let's plot it again. So first I'll call canonicalize S. And here already in the printout is visible that a lot of X's disappear. It's mostly Z's. And let's also plot it as a figure. You can see how the canonicalization indeed turned at least the x terms into an upper diagonal form, upper triangular form. The z terms were much more difficult to eliminate. That's kind of interesting fact here that given that you first need to eliminate the x's and you have only a square tableau, you're not left with enough pivots to eliminate the z's. There are a number of different canonicalization operations that are implemented, and they might be useful for different purposes. Some canonicalization operations are very useful for defining a partial trace. Some canonicalization operations are very useful for interpretation related to logical operations on their cracking codes. There are a number of different ones. There are canonicalization operations really interesting in terms of measuring the amount of entanglement in your stabilizer state. There is a ton of interesting canonicalization operations. You can see in the documentation of the library, many of them are documented with pretty pictures. Gaussian elimination. This is literally Gaussian elimination, but over binary numbers. So what did it do? It picked a pivot in the first column, and it removed all the x's from the first column. Then it went to the second column, and it removed all the x's in the second column, but starting one down. And it's nothing more than different variants of Gaussian elimination, but done over the field of binary numbers. I wouldn't use that phrasing. Another term that people use is reduced row echelon form. It's converting your list of linear constraints into a reduced row echelon form. It's doing the Gaussian elimination until the list of constraints looks as simple as possible. And because here you have both x and z constraints, you have a lot of freedom in choosing, do you do all the x's first, all the z first, x, then z, then x, then z? That's why there are different forms of canonicalizations, and you just need to pick one depending on the type of work you're doing. Okay, other questions? Yep.
Did you say something about how do you track phases when you're doing like characterizing these states, like after like these 50 operations?
Yeah, there is this column in front of the tableau of phases, of pluses and minuses. That's the only thing you're tracking in terms of phase information. Basically, whether you're the plus eigenvalue or the minus eigenvalue. And there is a little bit of an extra machinery to track that. On the other hand, a global phase is not tracked here at all. So these are really up to global phase. So if you have two independent sets of Clifford simulations and you want to keep a common phase between them, you cannot. The engine related, there's an arbitrariness in terms of the global phase of your simulation.
So is this getting this form is just starting with whatever first term is, then just multiplying that to the next one so that you remove the first x?
Yeah, what we did was we took the first row, we checked whether it had an x in the first column. If it didn't, we took the second row. If the second row has that, we swapped them, so it's now the first row, and all row operations can be done for free. And now we use that x, the pivot, to remove the x's from the entirety of the column by multiplying into the corresponding row. That way, we clean up all the x's from the first column. Then we're not permitted to touch the first row anymore, but we take the second row and we check whether it has an x in the second column. And basically, we do the elimination on the sub-tableau that excludes the first column and the first row. And we continue down the diagonal until we have cleaned up all the x's and x's are left only on the diagonal.
That guarantees that the pattern of the z's will also be unique.
Yes, it does guarantee it. I don't think it's an obvious statement though. Yep.
So running this a few times for a few different random stabilizers, it seems like there's sort of two species of graph that survive. There's one where, like the one you had, some x's and y's survive off the diagonal and it looks sort of stochastic. And then there's one where none survive and it looks very symmetrical about the diagonal. Is there something motivating that, or is that just?
I'm almost certain that it's something obvious. I don't know what it is. No, I don't have anything coming to mind. I don't think it's a deep or fundamental thing, but it's probably a fun factoid, but I don't know what it is. Other questions? Yep.
Could you theoretically simulate the IQP circuits, just the commuting part?
What's an IQP circuit?
It's instantaneous quantum polynomial time circuits. It's just Z's which commute with each other. So you're just like applying all the Z's at once.
Yeah, that sounds like something that would be very straightforward to simulate with this. I don't know what the IQP circuit though is, so maybe I'm missing something important.
But it also has Hadamard. It's basically used to show quantum advantage. And I was just thinking, just that subroutine of.
Well, let's go into dynamics. Now, we've been talking only about how do you represent a state. We haven't at all talked about how do you represent a gate acting on those states. And it's kind of useless to be able to represent states if you cannot represent their time evolution. So let's go into this second section, dynamics of Clifford circuits. And we'll finally also know why they're called Clifford circuits. So say we have the state psi. And what we're going to track now is not the state psi, but it will be the operator O, for which the state psi is an eigenstate. So we don't want to know how U is mapping psi to psi prime. We want to know how U is mapping O to O prime. So we are not asking for the rule for the time evolution of our state. We're asking for the rule for the time evolution of an operator for which that state is an eigenstate. So if psi is an eigenstate of O, I'm asking what is O prime such that U psi is an eigenstate of O prime. And this is a very common exercise when talking about Heisenberg picture. Basically, the rule for evolving a kit would look like this, while the rule for evolving an operator would look like this. You'll be conjugating your operator by U. Is this rule something that everyone has seen? Can someone gently shake their head if they would want me to discuss it a little bit more? Okay, let's take it for... Sorry?
Evolve the operator backwards in order to get the same results.
Sorry, could you repeat that?
I think that you evolve the operator backwards.
Did I do something wrong here?
No, you prime O, you drag O, U in the Heisenberg picture. I haven't seen it.
Well, now I'm not sure, so let's actually derive.
Let's check it.
It won't really be a derivation, it will be just a quick intuition behind what's happening here. Okay, thank you. Well, I believe you, but now I feel like I'm obligated to actually show that I know where this comes from. So there is this typical trick that you do where you multiply by identity, where identity is U dagger U. So let's just write a few eigenstate identities here. So I'm interested in, so we have this, and we also have O psi equals lambda psi. And well, let's just multiply the bottom equation by U. lambda by u. And well, this guy here is equal to psi prime. And this guy here, I can multiply it like this. I can do u dagger u. And this guy here itself is psi prime. So now I can write, instead of this in its place, I will write psi prime. Psi prime. And I'm missing a few lambdas. Let me just write them as well. So this is the new eigen operator. So are people comfortable with this? Did I make a mistake here? Okay, well, it would be really embarrassing if in a week someone looks at the recording and explains to me the mistake I made. But for the moment, looks good to me. I'm just waiting for the few folks that had the send. Okay, so this is the new eigen operator. So now, basically, my question is,
because when you calculate expectation values,
Mhm.
it should be the same. Like the expectation value of O, its psi prime should be the same as psi of O prime.
okay,
So then U psi will be here and U dagger psi will be here.
well, I'm too tired to follow what you're saying, so let's try to write it down. No. I like imagine how embarrassed I will be in a week if this is wrong. So let's just go through expectation value argument. So you're saying that we want this guy.
Psi prime.
We want this guy.
Psi prime should be equal to.
We are hopeful that this guy is equal to
Psi or prime psi.
yeah.
Which idea is that the above state, the expectation value of the operator
Yep.
on the above state should be the same.
That's perfectly reasonable. So let's do the thing here. I'm putting u, and here I need to put u dagger, and I can remove the primes. And yes, this looks like your thing. So
I think the reason is what we want is evolved operators acting on psi should be same as unevolved operator acting on evolved psi. In your case, you have U or U dagger acting on psi prime, not psi.
okay, but in my okay, that's a good point. What I want though is the thing I wrote, because I want this is maybe slight abuse of the term Heisenberg picture. What do I actually want? I want the operator for which the new state is an eigenstate. So this is a subtlety that I didn't know. So thank you for mentioning it. We shouldn't have skipped it. This is a subtlety that I'm actually really enjoying. It's not exactly what we usually think of as the Heisenberg picture, because I'm not tracking the observable. I'm specifically tracking the operator for which my state is an eigenstate. And this subtle difference, to me, is not particularly obvious. But I will delete this proper classic quantum mechanics Heisenberg picture, and I will stick to the more Clifford circuit style. How does the operator, how does the stabilizing operator evolve? Are we happy with that distinction? Okay. This was fun. Thank you. So now the point is, I have a way, an efficient way to represent Pauli operators. So my O prime better be a Pauli operator. If my O prime is not a Pauli operator, I cannot use my super fast data structures to run this simulation. So the only use that I will be permitted to work with would be used that map a Pauli operator to a Pauli operator. And that object is called the Clifford group of the Pauli group. And that's where the term Clifford circuit comes in. We'll be able to efficiently simulate only circuits made out of Clifford operations, operations that map a Pauli operation, a Pauli object to a Pauli object. There is an unsurprising theorem at this point that Clifford circuits are not general enough to represent any quantum dynamics. You need some other gate. It turns out that you need only one extra non-Clifford gate. Frequently, that's the T gate. So that's why you would frequently hear about Clifford plus T circuits, because that's a very convenient way to measure the quantumness of an operation. The amount of T gates is the amount of truly non-classical work you need to put in a circuit. But we won't be talking about the T gates until maybe the last 20 minutes. So we'll be talking only about Clifford gates. So now the next question is, sure, we might have something that maps Pauli to Pauli, so the initial state and the final state are in data structures that we can actually represent efficiently, but we're still not out of the woods. We need also an efficient to compute rule that takes U in some efficient representation and applies it to O. And that's now a new data structure that we need to figure out how to represent. And we'll really be leaning in the fact that we're representing Pauli operators as bit strings. And we'll be talking about the general linear group, the group of linear operations on binary vectors. That would be the group of Clifford operations. I know what I said sounds a little bit triptych right now. We'll go step by step through it. So everyone on the same page that U has to be what we call a Clifford operation for us to have any chance of simulating this efficiently, because O prime has to be a Pauli operation. Okay? Well, now we'll continue with some more decomposition. So here, every single one of those operators is an operator that acts on an arbitrary number of qubits, on n qubits. I will start decomposing things into single qubit operations. That would be somewhat important for me. And because I want to do something that's a little bit more hands-on and we can see numerical results, I actually will work through an example. I won't write down the general formula. I'll just work through it as an example. So the example is the following. Let's talk about P, X, Y, Z. I have this object, and I will be decomposing it in what I will call basis binary vectors. I want to decompose it into one-hot binary vectors that contain only a single non-zero term. So what would that look like? This would be, well, first we can do X identity times P, sorry, this equal here is not proper Julia equal. Let's put equal as a check. Times P identity Y identity times P identity Z. You agree this decomposition is unoffensive? Okay, then the next thing is this guy also needs to be decomposed. And up to phases, I really won't care about the overall phase for the moment. Up to phases, this is equal to do you agree with that statement? Up to a phase. Oh, thank you. Someone made a really discouraging phase, and that made me think I have an error. I did have an error. Do you agree with this up to a phase? Again, this is the binary tuple true false. This is the binary tuple false true. So the two together will be true true, which corresponds to Y. And now I'm interested in the following. I want U And again, this is not valid Julia code. I'm playing with writing a formula. And this would be equal to up to here, you agree? Nothing too surprising. I just put the simulator actually does, but I want to skip that. If I'm to care about that, I need imaginary unit or minus imaginary unit or something like that here. That I kind of just disregarded. The simulator does compute that properly, but this is something that I don't want to care about right now. And the last thing I will do is in between each term, I will multiply it with identity. And identity is u dagger u. So this would be u dagger u, u dagger u, u dagger u. And now I want to decompose this as in this form. So what did we do here? First, we decomposed our vector in basis vectors. And then we applied our operation on every single basis vector. And then well, I'm using the multiplication operation here because I'm working in terms of Pauli operators. But in terms of binary algebra, this multiplication is just an addition. So what did I do? I have a linear operator, the conjugation with u dagger, that I represented as a sum over the mappings of the basis vector. This is nothing more than matrix multiplication. X, Y, Z is my vector. It's a 6-dimensional binary vector. These guys are the basis vectors that this vector is a sum of. And the action of a linear operation on my vector is the same as the sum of the actions of the same linear operation on each of the basis vectors that represent my vector. And again, really think of this as a 6-dimensional binary vector, and think of this this multiplication sign as binary addition. So this object here is nothing more than binary matrix multiplication over a 6-dimensional binary matrix. And U will have some representation as a binary matrix. And what is a matrix? It's nothing more than the list of what the A basis vector will be mapped to. How do you think of linear operation? How do you fully define linear operation? You say what every single basis vector is mapped to. Each column of a matrix is nothing more than the image of the corresponding basis vector. So in that sense, let's pick yes?
A quick question, maybe I missed this. Why did you want to decompose the original string into operators that only have a single root?
Because I wanted to introduce the notion of a basis vector, nothing more than that. I wanted my basis to be kind of the obvious basis, the basis of one-hot vectors. And this is a basis vector in the binary space of the binary representation of Pauli operators. This is another basis vector, this is yet another basis vector, and yet another basis vector. And all I'm showing here is that this looks a lot like matrix multiplication, where matrix multiplication is basically applying the linear operation to weight times a basis vector, and then summing up those images of the corresponding basis vectors. So if we can define a linear operation in terms of the mapping of the basis vectors, we can compute this. And that's what I will do here with an example of the CNOT operation. T CNOT for Tableau CNOT has its own pretty printing, but think of this as a binary matrix that maps the basis vector x acting on the first qubit to the vector xx. It maps the basis vector x acting on the second qubit to identity x. It maps the basis vector z acting on the first qubit to z identity. and it maps the basis vector z acting on the second qubit to zz. So now if I want to compute if I want to compute C0 on the state, let's pick something slightly interesting. So C0 on the state plus 0. I want to compute this. Well, first, what is the stabilizer tableau representing this guy? The stabilizer tableau representing this guy would be S X identity Z, right? And I will need to take this vector, which thankfully is already a basis vector, and map it. And take this vector, which is also already a basis vector, and map it. So this guy is this guy. It will be mapped to this. And this guy is this guy. It will be mapped to this. So my resulting state probably will be XXZZ. Let's see whether this is true. TC0 acting on SXIIZ is indeed that. Let's do something slightly more complicated. Let's do TC0 acting on that exact state again. By the way, this is the Bell pair state. It's the state that's stabilized by two non-local operators. Okay, so what would happen if we act with TC0 twice? C0 times C0 is the identity operation, so we better get back the initial state. Well, let's see why that would be true. This guy is equal to X identity times Pauli identity X for the first row, and P Z identity times P identity Z. This is a notation that's natural for this programming language, not necessarily mathematically natural notation. But what do I have here? I've decomposed the first row of the tableau into basis vectors. The basis vector xi and the basis vector ix. And I decompose the second row of the tableau into basis vectors. I need to apply TC0 to every row of my tableau. So I will need every row to be decomposed in basis vectors. So what does ix get mapped to? Well, ix, so first row. What does xi? What does xi get mapped to? xx. And what does ix get mapped to? Still ix. So the mapping will be first row after TC0. xi, as I mentioned, gets mapped to xx. So this will be xx times p ix gets mapped to ix. And what's the product of xx and ix? Well, x and I is x, and x and x is I. So this guy is just equal to p xi, right? And second row after TC0 is equal to, what does zi get mapped to? Zi gets mapped to zi. What does iz get mapped to? To zz. And z times z is identity. And identity times z is z. So I would hope that this guy, after I act with TC0 to it, will become xi iz. Well, let's see. TC0 acting on S XXZZ is indeed X identity Z. And I want you also see this very explicitly, that internally it's implemented through the equivalent of a binary matrix multiplication. It might be a particularly highly optimized binary matrix multiplication that acts on the bits of large words, but it is just binary matrix multiplication. So to do that, I will actually use a function that explicitly shows me the binary structure of these matrices. So there is this function called stab2gf2 for Galois field 2. TC0, actually no, let's do P XX. So this will just give me the binary vector representation of XX. 1, 1, 0, 0, nothing too surprising. So let's go for something more substantial. What is the binary matrix representation for the CNOT tableau? Stab to GF of the tab is just a helper function that extracts the internal tableau from the CNOT, because Clifford gates themselves are represented as a tableau. Notice that the Clifford gate is nothing more than a tableau that's slightly longer than the others. It's a tableau of twice the length because you need mapping for every single basis vector. So let's get the binary representation of TC0. It's this matrix here. And if you look at this matrix, it is nothing more than this tableau represented in binary. And then let's do the same thing for the stabilizer. Here I'll have only one row to simplify things a little bit. We'll be focusing only how one of the rows gets modified. This doesn't define a complete state. But again, I'll just extract its binary representation. And it's XY, so both X terms are filled in, but only one of the Z terms is filled in, okay? So questions up here about these two vectors, the binary representation of the CNOT tableau and the binary representation of this single row of an XY tableau.
So what does the single quote do at the end of step?
A transpose, because internally, if I want to do matrix multiplication, I just need to make sure that my rows are aligned with my columns. It's just addressing the fact that internally something might be transposed. Yep.
Just to check if I understand. Basically, the matrix, the 4x4 matrix is just the first column is IX and it maps to XX, XI maps to the next one, IZ, ZI.
Yes. And now let's just do the binary matrix multiplication. And the nice thing about matrix multiplication in binary is that you can just use the default floating point matrix multiplication and just do modulo division by 2. That kind of turns it into a binary operation as well. So let's check what this guy is. And let's see whether this is the same as TC0 acting on SXY. So stab to GF2. It's indeed the same matrix. So, well, the same vector. Why am I showing this? Just to reiterate that internally, applying a Clifford operation is nothing more than first making sure that the Clifford operation can be written down in the form of a list of mappings of the basis Pauli binary vectors. And then the rest is truly just matrix multiplication, but over the binary field. And remember, the matrices, if these were unitary matrices, would be exponentially expensive, while here they're just linearly expensive. Yep.
Every state, or maybe a product state, a stabilizer of something.
No, very few states are stabilizer states, but all code words of quantum error correcting codes and all error words after measuring the observables of a quantum error correcting code are stabilizer states, which is why this technique is so extremely important for modeling error correcting codes. Without this technique, we wouldn't know which error correcting codes are good and which are bad, This is letting us study the performance of thousands of qubits error correcting codes on a classical computer.
Can you say that again? I just like how you said it, so I want to write it.
Okay, I'll try to remember what I said. When talking about error correcting codes, a code word of an error correcting code will be a stabilizer state. An error word of an error correcting code, which is the state of the system after you have measured the observables related to the error correcting code, is also a stabilizer state. So even though many types of noise will be moving you from a stabilizer state to something that's not a stabilizer state, this technique is sufficient to model anything related to error correction because the error correction procedure itself forces you back into a stabilizer state. Most states, the space of kets is continuous space, so it has infinitely many kets. And the space of stabilizer states is a discrete space, so it has finite amount of stabilizers of states. So there's infinitely more states than stabilizer states. But nonetheless, stabilizer states pop up in many extremely important situations. And now we have the representation that's efficient. We know how to represent a stabilizer state. And we know the class of operations that are efficient to simulate on a stabilizer state, the Clifford operations. And we know how to represent them and to efficiently simulate them, apply them. Question?
Are stabilizer states being used in error correcting codes because they're easy to simulate, or is it just like general enough to do that?
I feel like this came from two kind of separate directions. People noticed this nice property of the Pauli group and the Clifford group of the Pauli group, and they figured out that stabilizer states on their own are useful. Roughly at the same time that people noticed that classical binary error correcting codes are a natural way to introduce quantum error correcting codes, and the two formalisms happen to be basically the same formalism looked at from two different sides. I'm not directly answering your question, but historically, I think that's what happened. All of it in the second half of the 90s and the first few years of the millennium. Other questions? Yeah.
Are there states that are stabilized by non-Cliffords that are useful in quantum information stuff?
There are some more esoteric versions of something like this. There's a whole Clifford hierarchy, and people do study those. They're not the workhorse of quantum error correction, though. And I just don't know much about them. So they're certainly useful, but not as in vogue.
Yeah, I was just wondering because I haven't heard much about them. So yeah.
Yep.
My question was a bit similar because all of the reason we are able to do this efficiently is because of the conjugation rules. Like for CNOT, like you can just conjugate all the poly and then you can describe them. So like I guess you said there's a hierarchy, so you can keep doing this. You can just keep conjugating whatever gate.
Yeah, there is the Clifford group of the Clifford group of the Pauli group. But then you have the difficulty that the thing that you're acting on now doesn't necessarily have as nice of a representation, and the action itself doesn't necessarily have as nice of a representation. So it's not just the conjugation trick, it's also the fact that the Pauli operators are so trivial to represent. Other questions? Okay. So we haven't talked about measurements. That's maybe another important topic. We haven't talked about gates that are not necessarily multi-qubit gates. We want to see also how do you apply a 2-qubit gate, a 1-qubit gate, these building block gates. Those are things we can discuss. And another thing we can discuss is just jumping into error correcting codes. My feeling is that we do have the measurements as a prerequisite before we can talk about error correcting codes. So we probably won't go to error correcting codes, but let's focus on not only how do you apply a unitary operation, a Clifford unitary operation, how do you perform a measurement in this formalism? Okay, so before we continue though, I want to mention one thing. Here, TC0 was happened to be a 2-qubit gate, and it acted on a 2-qubit state. Most of the time with error correcting codes, we'll have a state of 1,000 qubits, and we would want to act with a 1-qubit or 2-qubit gate on a specific pair of qubits. So we need that part of the API, and QuantumClifford, Steam, TSIM, Clifford, all of them have some set of predefined gates that are actually not represented as an arbitrary tableau. After all, if we're acting with an arbitrary tableau on an n-qubit state, we would need a large n-qubit tableau in which most of the terms are zeros. So instead of that, we would have some API for acting with a small gate. And frequently those small gates will not be written down as a tableau, rather they will have some hard-coded internal representation that traverses the tableau and performs a computation of its own. This is frequently called a kernel. All of this doesn't matter too much besides just talking about the API for that. So say I have a random stabilizer state of 100 qubits. How do I act with the CNOT gate on the 5th and 50th qubit? So this is my state. This is my state here. And again, there's some skipped rows and some skipped columns because it's too large. And I want to act on the 5th and 50th qubit. To do that, one option is to take the T-CNOT gate and pad it with T identity 1 many times. And obviously that won't be pleasant. And more importantly, it won't be efficient. Every single time I'm applying a gate, I'll need to create a temporary object. So for common gates, most of these simulators have kind of a more opaque symbolic object. Here they happen to be called S and then the name of the gate, and they'll have some form like that in other simulators, where you basically generate a very compact structure. The structure here is really nothing more than the name C0 and the indices 5 and 50. It doesn't have a tableau behind the scenes. It's purely symbolic object, and there's a special method that's implemented specifically for the type C0. That's why multiple dispatch is so cool here, because you can just define a method for this that computes the action of C0 by taking out qubit 5 and qubit 50. Actually, I'll show you the code. It's not particularly important to understand the code. I just want to give you a flavor of how something like this is implemented, stressing that it's not implemented by writing down the tableau and then building a larger tableau out of it. So let's do edit SC0. And here is how SC0 is implemented. SC0 is implemented by defining some kernel that knows to take the X1 bit and put it in the X1 location, to take the Z1 bit and the Z2 bit and to compute their XOR and to put them in the X2 location. And it's basically a hard-coded version of the tableau. On one hand, it sounds kind of stupid to hard-code it, but because by hard-coding it, it's drastically more efficient and it doesn't require you to create the actual tableau. If you just have some small set of important assembly gates, it's much more efficient of a simulation method. So really think of this as if you took the tableau and wrote by hand the the result of applying the tableau. And if we look at TC0 and compare it to this, well, what does this x1 mean? It means that the x1 term of the output can only come from the x1 term of the input. What does this here mean? That the z2 term, sorry, just a second. The z1 term of the output, depends on the z1 term and the z2 term of the input. So it's really nothing more than a hard-coded version of this tableau. And if you implement it that way, you can skip some annoying preparation of general purpose objects. The general purpose object would be just too heavy here. I know I'm repeating myself at this point, but in any such simulator, there will be a hard-coded version of the common gates. And distinguishing between them, being aware of this distinction also probably would lead to higher performance. So we have apply S, the random state, S CNOT 550. This applies it, and let's just see how fast this is. It's taking 12 microseconds, and compare that with time apply S, and then I'll do TC0, and I'll do it only on the first and second qubit. TC0 all times tensor power of T identity to the power of 98. So what do I have here? I have 98 identities tensored with TC0. So I just want to, this is much less pleasant to write, but this is how I prepare a large 100 by 100 tableau. And let's just run it twice. This is half a millisecond versus 12 microseconds. So that's why these simulators have hard-coded versions, symbolic versions for a lot of their gates. Questions about this distinction?
So is there ever a time you would want to use TC0?
TC0 on its own, no. But if you want to store the action of the circuit, as opposed, not the circuit as a gate-by-gate representation, but the circuit as one big Clifford operation, that's a situation in which you would want the general purpose tableau representation.
Okay, so like when you're composing it with other gates,
yeah,
then it does.
It's not obvious that you would prefer to have the composed representation. In many situations, it's more convenient to have the circuit representation, but maybe you have two different circuits and you want to check whether they're the same circuit. Then have the big composed representation will be convenient because you can compare those directly, while two different circuits might be implementing that's the same big composite operation.
Thanks.
Other questions? Okay, well, let's do the last thing. If we end up a little bit early, great. You go to bed earlier. If not, well, the night is young. Okay, so let's finally focus on measurements. This library, any other library for Clifford simulations, would have some function that performs the measurement for you. In this particular library, it happens to be called project. And yes, it's only Pauli projection measurements. It's the only thing that's efficient to simulate in that formalism. And you measure only in a Pauli basis. in a basis of Pauli eigenstates, in an eigenbasis of a Pauli operator. You only distinguish the two projectors representing the two eigenprojectors of a Pauli operator. So you'll be basically measuring the eigenvalue of a Pauli operator. And the API is fairly straightforward. So let's say we have the state X, an eigenstate of the X operator, and let's say we measure it in the Z basis. We measure it in the basis of the eigenstates of the Z operator. Our measurements always will be extracting one bit of information. So they won't be measuring every single one of the qubits. They'll be measuring a Pauli observable. And the resulting state will not be a factorized state. The resulting state will be projected on one of the two possible eigenspaces of the Pauli observable. So if we have a state that's the eigenstate of the operator X with the eigenvalue +1, the state stabilized by the operator X. I'll stop saying eigenstate of yada yada with eigenvalue +1. I'll start saying stabilized by. If we're measuring, if we're projecting, if we're doing a projective measurement on the state stabilized by X, and the projective measurement is measuring the operator Z, will that be deterministic or probabilistic result? Our basis is the basis of eigenstates here. It would be the measurement result would be either 0 or 1. And our state is the plus state. Is this a probabilistic or deterministic result?
Probabilistic.
I'm hearing some murmurs about probabilistic, and that's true. And I'll actually project as kind of a low-level function. You can check the docstring for it for exactly what it means. I'll go straight for projector rand that if there is a randomization, it applies the randomization as well. It returns a few things, a couple of things. One of them is the stabilizer state. The other one is the phase. But I will just get only the stabilizer states. And I'll run this a couple of times just to see the results. We get plus Z, minus Z, minus Z, plus Z, plus Z, minus Z, minus Z. Okay, if we do the measurement a bunch of times, we see that it's probabilistic. What about this guy? Will this be probabilistic or deterministic? We have an eigenstate of the operator Z. We're measuring which of the two possible eigenstates of the operator Z it is. It will always be that same eigenstate. Okay, let's do something that's slightly more complicated. Let's do the Bell-state, ZZXX. What is ZZXX? By the way, let's just make sure that everyone's on the same page about what ZZXX is. It's the superposition of 0, 0, and 1, 1. Is the thing stabilized by ZZ? And indeed, 0, 0 is an eigenvector with eigenvalue +1. 1, 1 is an eigenvector with an eigenvalue +1. So their sum will be an eigenvector with an eigenvalue +1. For XX, it's a little bit less obvious. XX maps 0, 0 to 1, 1 and 1, 1 to 0, 0. So XX acting on 0, 0 plus 1, 1 is 1, 1 plus 0, 0. And plus doesn't care about order. So this is an eigenvector as well. And let's measure in the Z basis on the first qubit. So what are we doing here? We're basically measuring only the first qubit. Identity on one of the qubits means that we're just not caring about that qubit. Identity has one eigenspace. Everything is stabilized by identity. So if our projective measurement involves identity on one of the qubits, that qubit is not really touched by that measurement. So what happens if we're measuring in the Z basis the first qubit of a Bell-state? What should the result be? First, is it probabilistic or deterministic? It's probabilistic because if you have 0, 0 plus 1, 1, when we measure the first qubit, we'll either get the 0 branch or the 1 branch. Interestingly though, the measurement leads to something happening to the second qubit too. Because of the correlated state, if we measure the first qubit, we know what the second qubit is. So let's see what this looks like in terms of a projective measurement. So what is this guy? What state is this guy? Someone said 1, 1. They're right. How would I go to see that? Well, the second stabilizing operator is a little bit easier to deal with because it acts on one single qubit. And the only thing stabilized by this guy would be if the first qubit is the state 1, because 1 is an eigenvalue -1 for the z operator. So it would be eigenvalue +1 for the -z operator. What about the second qubit? Well, the easiest way to see it is to take this guy, multiply it into this guy. So this sign becomes minus. This z, the first z becomes identity. So this row will become minus identity z. And by same logic, the second qubit has to be 1. And let's run this again. Well, there's no minus now, so it's 0, 0. So we're either getting 0, 0 or 1, 1. So now, well, let's focus on how the computer figures this out. Any questions before we jump into the algorithm? Yeah.
So if you, instead of zi, if you just put z, it still calculates?
So this is kind of ill-defined.
Yeah.
There will be an API that makes this more pleasant to work with. There happens, in this particular software, there happens to be an API apply to the state S, ZZ, XX, apply the symbolic measurement S, measure Z on the first qubit. You can do that. But at this point, I'm just talking about the API of this particular software. Like, I love this particular software, but the API is not important. The general idea of how these tools work is what's important. So yeah, because this is more of a low-level linear algebra API, project RAND, it's really, think of it more as a linear algebra 2 over binary vectors that happen to be written in this weird physicsy way of letters instead of binary numbers. Think of it more as a linear algebra 2. In a linear algebra 2, you wouldn't multiply a 2-dimensional matrix with a 1-dimensional vector. So let's keep the I. Okay, so let's do it. Let's do it by hand for a particular case. Let's start with project RAND. The thing that we started with, the state stabilized by X, measured by the operator, measuring operator X as well. So here, what the software should do is should check whether the measurement operator commutes with all of the stabilizers. The measurement operator is X. We have only one stabilizer, X. They commute. So we now know, the simulator knows that the result will be deterministic. That's actually the annoying case. That's the difficult case. Now that the result is deterministic, what we need to do is to represent our measurement operator in terms of products of the stabilizing operators. And we see whether there's a mismatch in phase. If there is not mismatch in phase, we have a phase, we have a result with value +1. If we have a mismatch of phase, we have a result with value -1. I spoke pretty quickly here. I just wanted to give a flavor of this. Now we'll actually do it manually for an interesting large case. So let's have this state, XXX, ZZI, IZZ. This is the state we have, and we'll be measuring the operator. We're measuring the operator ZIZ. So what does the software do now? The software checks, does the first row of S commute with the operator we're measuring? Well, does it? Com of S first row and P. There's an anticommutation on the first qubit and an anticommutation on the second qubit. Two anticommutation add up to one commutation.
Will we get a valid stabilizer?
Good question. Let's go through that. Does XXX and ZZI commute? X and Z don't commute, X and Z don't commute, X and I commute. Two anti-commutation add up to a commutation. As long as the mismatches are an even number, the things commute. Z's will be commuting with Z's, and the first row does commute with the second, and the first row does commute with the third. This is a valid stabilizer. This happens to be the GHZ state of 3 qubits. This is 000 plus 111. Let's actually see that. Ket S. It's a superposition of the first basis vector and the last basis vector. So, okay, my question was, does the first row and the operator that we're measuring commute? It commutes. Does the second row commute with the operator we're measuring? It commutes. Does the third row commute with the operator we're measuring? It commutes. So after this check, how expensive was this check? This was a quadratically expensive check because for each row, we need to check something involving the entire row. So we need to go through all of the data of our Tableau, quadratic amount of data. So after this quadratically expensive check, we know that our operator commutes, the operator we're measuring commutes with all the stabilizing operators. We know that the state we have is already an eigenstate of the operator we're measuring. Okay? So now that we know this, we need to start doing row operations until this stabilizer Tableau has this guy as one of its rows. There is a canonical way to do that. We will see the canonical way, but let's do the hand wavy way of doing that first. What happens if I multiply this row into this row? I get another stabilizer. Let's go at S1 equals to S XXX, and I said I'm multiplying the third row into the second row. I get ZIZ. And then for the last row, I keep the last row IZZ. Do you agree that the state S and the state S1 are the same state, just represented in a slightly different manner? Okay. Row operation is for free. It doesn't change the state. If something is an eigenstate of A and an eigenstate of B, it will be an eigenstate of A and B. And if the eigenvalue is +1, it will be an eigenstate with the same eigenvalue. So all I did was rewrite the Tableau in an equivalent form. But importantly, this equivalent form involves explicitly the operator we wanted to measure. And we can already read out the eigenvalue for that operator. There is implicitly a plus here. So the measurement result would be +1. It would be the eigenvalue +1. So now the annoying thing is, if you have a 50 by 50 Tableau, how do you do this thing I just did? How do you figure out what rows to multiply together in order to get the phase? Well, what you do is you actually take S and write S, let's call it SP, which is, you write this larger than necessary Tableau, XXX. You copy your Tableau state, IZZ, ZZI, IZZ, and you add as an extra row ZIZ. This is the operator you're going to measure. Now you do Gaussian elimination on this guy, which is basically using these rows in order to clean up the rows underneath them. And as you're doing this, at the end of the Gaussian elimination, this row would be a row of identities, potentially with a non-trivial phase in front of it. That phase would be the measurement result. This is the trick that lets you, Gaussian elimination is the trick that lets you represent one row in terms of other rows. And how expensive is a Gaussian elimination? For each pivot point, you need to go through the entirety of the column. And as you're going through the entirety of the column, you're doing something with the entirety of the row. So n pivot points, n columns, n rows, it's a cubic operation. A measurement is a cubically expensive operation. If you have done the check, the quadratically expensive check, that tells you that your measurement commutes with the state you have. And that's a difficult case. If you know that your measurement commutes, you need to figure out how to represent your measurement operator in terms of products of the stabilizing operators. Now, let's go to the other case. Questions up to here? Just for me, can I get some thumbs up if you still have energy and are actually following what I'm saying, and thumbs down if you're running on fumes. And please don't be shy. This is valuable feedback. It informs how I'm going to continue talking. So, okay, I'm seeing a couple of people doing this, which is...
I think it's thumbs down, but they're too shy to say it.
Sorry, what?
I said it means thumbs down, but they're too shy to say it.
Yeah, yeah. Yeah, that's fair.
I was wondering if the last phase is always 1 or -1.
It can be -1.
Can it be I?
No, because these operators are commuting. If they're commuting, you cannot get an I. Again, that emerges from the multiplication rules for Pauli operators. If two Pauli operators commute, the fact that they're commuting is why I'm permitted to do this multiplication. If they're not commuting, I will need to know, am I multiplying a row from the left or from the right? And because that will be giving different results. And it just, the consistency evaporates. Because they're commuting, I'm permitted to do these operations. And because they're commuting, I know the result will be either -1 or +1. Yep.
So when you do this multiply trick and rewrite the second term to ZIZ, then what is the difference between if you just change the i's to z in S? So if you had ZZZ and then all z's, and then you multiply and then you still get ZZI, which you can write as ZIZ, but then you get different state, different get.
I'm sorry, I didn't follow.
So in S, where you have ZZI, if you just change the I to Z in both of the terms. Oh, I mean, I to Z. So it's all Z's.
This is a different state. ZZZ cannot be obtained from ZZI and IZZ. So if I have this guy, well, first of all, this is not a valid stabilizer state because the first and second row don't commute. However, kind of related question, what if I'm measuring an operator that doesn't commute? So what if I'm measuring, instead of measuring ZIZ, I'm measuring IXI. Let's start a quadratic check. IXI commutes with the first row, so I go to the next row. IXI does not commute with the second row. So I know that any information conveyed by this row is going to be deleted by my measurement. So the quick, naive thing to do is to just delete this row and in its place to write IXI and then plus and minus in front of it because it's 50-50 what will happen given that I'm measuring a non-commuting operator. But then I go to the next row. The next row also anti-commutes with this guy. So I need to do something before I did this deletion trick. So as I'm doing my check, I have this, let's call it S prime, which is XXX. I'm just copying it because it commutes. ZZI, I mark it as the first non-commuting row. And then I have IZZ. This row also anti-commutes. So what I want to do is to remove the anti-commuting part from it. What I'm going to do is, because row operations are free, whenever I have not first anti-commuting row, into it, I will multiply the commuting row. So I will multiply this guy that contains anti-commutation with respect to my measurement operator into this row that also contains anti-commutation with respect to my measurement operator. And this row will become ZIZ. And the anti-commutation canceled out. This row also commutes. So now, after I do this quadratically expensive operation of scanning through my rows, finding the first non-commuting one, and cleaning up the anti-commutation from any other rows, I'm left with a tableau equivalent to the initial tableau, in which only one single row anti-commutes with my measurement operator.
Multiple of non-commuting, we pick the first one and just.
Yep, that's all. And now that I have only one location where all the anti-commutation is stored, I am finally permitted to do IXI, and then I need to add some random phase here with plus or minus. And that's the cheap case, by the way. Notice that here we had only a quadratic cost to do that, because the Gaussian elimination was the expensive thing in the previous case. While here, while scanning, questions up to here? So that's it. Measurement operation in the case of a commuting operator is a bit more expensive because we need to figure out how to express the commuting operator in terms of the stabilizing operators. And in the case of a non-commuting operator, it's just quadratic, not cubic, because you just need to consolidate all of the anti-commutation in a single location and to delete that single location. Okay. And then the last thing we can discuss is this additional feature you can add to the stabilizer formalism, making it into the destabilizer formalism that lets you make both checks be quadratic in cost instead of cubic. So with a little bit of pre-computation, we can actually skip the Gaussian elimination. Before we do that, that probably will take us about 20 minutes. We have about 35 minutes. Do you guys prefer to take a 5-minute break or to power through this last part? Okay, let's do a 5-minute break and reconvene exactly at 10. Sorry, I couldn't hear you.
Going after 5 minutes.
There's some not in the mentioned method. And in general, also no. However, there are simulators that permit you to do T-gates. And with a T-gate, exponentially expensive in the number of T-gates. So one T-gate, so 10 T-gates will start being pretty bad. Not substantial. Like there are certainly optimizers that figure out how to move something somewhere. Those are really cool. But they won't factors. They won't substantially change the cost. But now that you have such a simulator that permits T-gates, well, if you want a measurement in non-poly basis, just figure out the non-Clifford operation that maps that basis to the poly basis. And you have now, instead of your general measurement operator, you have a bunch of T-gates followed by a poly measurement. But now you need to simulate these T-gates. So, strictly speaking, yes, you can do it. But you do it by figuring a change of basis into the poly basis and using a more expensive simulator. Yeah. Like something like a risk measurement or sorry?
But yeah, you can go as
I'm sure there are ways you can drive that. Probably you can do something like turning the into a circuit that involves and projected measurement. Then you simulate the gates and the projected measurement. So the answer is again yes, but by rewriting it in a way that involves a projected measurement that's not for it.
That's what I don't think it's too far. Okay, that's for 2000.
And then I'll add that here.
Okay, then you make a guess. 1967. Members of Rami joined clubs carrying okay, this I would not have. But there are so many country flags. No, I guess there's only one country flag multiple times. Oh, okay, based on how far off we were, we got zeros. But you got some decent points.
I have these figures like this.
So there are 5 such.
And then the rest of these though are all right together.
Let's go look at this pattern.
This has a more regular rectangular structure to the data structure. So it's simpler, faster.
You have to like
The example is more general. It's much more messy data structure that you need to choose.
So that's how it works. And then it goes
Fairly related. The example is more general.
But here I think it's right now.
No, the graph state is not really related. The graph state is just stabilized.
Heavily underestimated.
Right after World War II. Because these were left over by
it's nice
Germany.
that
So this is right after We're 7 years off. And I 1.6.
This is English. That's good.
Western automotive.
Western English.
Western English. So this is US World War II, I think.
Good as it
Usually we end up dropping these.
My guess is 60.
The simulator is low, but it will also need to randomly pick whether it's a plus or a minus.
Where is the US?
Okay, my guess is
Okay, let's continue. So there is one more data structure that I want to show you. So we have this S tableau, the stabilizer tableau, and a defining property of this tableau was that its rows were commuting. They need to be commuting for this to be a well-defined data structure, representing an actual state. There is another slightly more general data structure. It has a contrived name for reasons. Mixed destabilizer of S. Let me just clean this up a little bit. So this is S, and I have mixed destabilizer S. Oh, apologies, it's using dots to complete it because it's a bit too large for the screen. Let's try again. We have S and mixed destabilizer S, and finally it actually shows up. So do you see it on the screen? Is it visible enough? Okay, so what is this new data structure? So the stabilizer, there is some canonicalization operation on the stabilizer, but the stabilizer part marked with stab, it's the same. XXX and then ZZ, and then it happened to do canonicalization while it was converting it to this general data structure. But this tableau here is equivalent to this tableau here. The stabilizer part of the mixed destabilizer data structure is the same up to canonicalization. A more interesting part is the second part of the destabilizer tableau, the destabilizer part of the tableau. What is the defining property of this object? Well, its rows also commute. But importantly, they element-wise anti-commute with the rows here. So there's always, for a stabilizer tableau, a way to compute the corresponding destabilizer tableau. Surprise, it happens to again be Gaussian elimination. So it's a cubically expensive operation. And the destabilizer tableau, again, I'll just repeat the properties. Rows in this part of the tableau all commute. Same as we always want rows in this part of the tableau to always commute. But the first row here anti-commutes only with the first row here. The first row of the stabilizer part anti-commutes with the first row of the destabilizing part. The second row anti-commutes only with the second row. The third row anti-commutes only with the third row. And the first row will be commuting with the second and third row here. So it's really a pre-computed, distilled storage of the anti-commutation that you might have access to. So when you're doing a measurement, as usual, you will scan through the stabilizer part and you check whether you're commuting with all of them. If you're not commuting with all of them, you do the operation we described, you delete one of the rows, and that's it. Quadratically expensive operation. Nothing changes there. But this is particularly useful when working with the commuting case. Say that you have a measurement operator IZZ. You scan through this part of the tableau and you see that it commutes with this guy, it commutes with this guy, and it commutes with this guy. You did your cheap quadratic scan, and now you need to do the expensive cubic Gaussian elimination to figure out how to express this guy. But because you have pre-computed the destabilizer, you can actually skip that part. Now you start scanning the destabilizer. And in the destabilizer, you see that you commute with this guy, so you skip it. You don't care about it. You anti-commute with this guy, so now you know that this row is involved in how you need to be represented. And you anti-commute with this guy as well, so now you know that this row is involved in how you need to be represented. So this is basically a trick that skips the Gaussian elimination and directly tells you which rows of your tableau you need to multiply together in order to obtain your measurement operator. And thus, again, just by doing a scan instead of an expensive Gaussian elimination, you immediately find the the eigenvalue for your measurement operator. So just to repeat it, you measure through here, you scan through here. If you see that you don't commute with someone, it's the same trick as previously discussed. If you see that you commute with everyone, you scan through here, and for the terms that you're anti-commuting with, they mark the fact that you need to, you will be expressed, your measurement operator will be expressed in terms of the corresponding stabilizer operator. It's a neat trick to pre-compute the effect of the Gaussian elimination. And you need to do this only once at the very beginning. And actually, if you're doing it at the very beginning, you know what the destabilizers will be. If at the very beginning, your stabilizers are a diagonal of z's and your destabilizers are a diagonal of x's. So you don't even need to do Gaussian elimination at all if you're simulating a circuit from some initial state. And that's it. That's the destabilizer formalism. This pre-computation trick that uses double the amount of data, but lowers the cost of a commuting measurement from cubic to quadratic. Any questions?
Can you make a practical example? Like say pick, we measure IXI, how would we do it with that state?
Yeah, let's copy this guy. So here, I want to measure this guy. I'm specifically picking this guy because it's not obviously one of the stabilizing operators. So I'll need to figure out how to express it in terms of stabilizing operators. Actually, let's pick this guy just to have something slightly less trivial. So what am I doing? This is my measurement operator. I'm scanning the stabilizer part. It commutes with this guy, so nothing to do. It commutes with this guy, nothing to do. It commutes with this guy, nothing to do. Oh no, this is the terrible, expensive case where my measurement operator commutes with all my stabilizing operators. Now I need to figure out how to express my measurement operator in terms of the stabilizer operators. If I didn't have the destabilizers, now I will be doing expensive Gaussian elimination. But I have the destabilizers. So I check. I scan again, but this time through the destabilizers. Does my measurement operator commute with the first destabilizer? It does. I don't care about it. I go forward. Does it commute with the second destabilizer? It does not. So now I take this guy, the corresponding stabilizing operator, and I multiply it into my measurement operator. What is ZZ identity times IZZ? Well, ZN identity is Z. Z and Z is identity, and identity in Z is Z. So I just updated my measurement operator. And I continue. I go to the third term. The third term also anti-commutes with my measurement operator. So given that the third destabilizer anti-commutes with my measurement operator, I take the third stabilizer and I multiply it into my measurement operator. Z times identity is identity. Identity times identity is identity. Z times Z is identity. And my measurement operator becomes minus identity, identity, identity. I just finished expressing my measurement operator in terms of my stabilizers without having to do Gaussian elimination. I'm left with a phase of -1. That means that the overall measurement result, the eigenvalue, will be -1. So again, the moral of the story is that having access to these destabilizing operators lets you, for much cheaper, know which of the stabilizing operators you need to multiply together in order to obtain your measurement operator, skipping the need for the Gaussian elimination, which would have been cubically expensive. Yeah.
Is that something that this package will automatically do for you if
Yeah.
the thing is big enough?
So let's show that. Let's take S. Let's do S as some large random destabilizer. Random destabilizer of 200 qubits. And let's not print it. Actually, I'll call this DS for random destabilizer. And I'll also have S equals random stabilizer of 200 qubits. And now what I want to do is to measure how expensive is it to do at time project rand S. And I will be measuring the first row of S. Sorry. I'll type it here so that it's visible online as well. At time, project S, and my measurement operator MS will be the first row of S times the fifth row of S times the 166th row of X. So MS. I want to see how fast the projection will be if I'm using the stabilizer data structure that doesn't have this thing pre-computed. And I on purpose prepared a measurement operator that commutes with all my stabilizer operators. I'll just do this once to make sure that it precompiles. Oops, I haven't defined what MS is. Okay, and now let me actually run it. So this took about 2 milliseconds. And now let's do the same thing for measurement with the destabilizer, where I have stabilizer view of DS, the first and the fifth and the 166th. This is saved. It should be showing online. Let me just run these again, and let me run these DS and MDS. I'll just run these things once to make sure that things are compiled. I don't want to measure compilation time, and let's run them again. Let me clean this so that everything is neat. And so now that I have my benchmark set up, I'll be running the measurement of a commuting operator using the stabilizer formalism. It took about a millisecond, and gosh, it would be embarrassing if this is not faster. It took about 20 microseconds, so it's faster. How did this work? Well, if we look at methods for the project function, it has a method defined for it has a method for, no, this is not very clear. Let me just clear this. How did this work? How come one of these was faster than the other? Through multiple dispatch, somewhere in the dispatch tree of these methods, project on mixed destabilizer used a special dispatch that used the pre-computed information in the destabilizer data structure, while project on stabilizer didn't have access to this data structure. So the difference is that the type of the data structure S is this stabilizer object, while the type of the data structure DS is this destabilizer object that has this extra part of the tableau, and the code of various methods of various functions know how to utilize the pre-computed information in the destabilizer. For instance, you would implement that by having function project acting on destabilizer, and you have the code for that. and you have another implementation function project on stabilizer, and you have the code for that. And whenever project notices that you're giving it a destabilizer, it will use the optimized method that uses the pre-computed results stored in the destabilizer.
So the destabilizer structure then includes a stabilizer tableau and its corresponding pre-computed destabilizer tableau?
Yeah, we had this example here.
Oh, yes.
S equals GHZ on 4 qubits. This is a stabilizer, and we can convert it to destabilizer, where it pre-computes the destabilizer part of the tableau. So yes, the destabilizer data structure contains this extra information, the destabilizer tableau.
I was under the impression for a second that destabilizer was just the destabilizer tableau, but it makes sense that it's
bad naming conventions that we're now stuck with. Yeah, stabilizer view is just a helpful method for well, destabilizer, let's call this DS. Stabilizer view is just a helpful method to extract the stabilizer part of the destabilizer.
MGS and MS differ?
This is so first thing just to mention here, now I'm kind of describing the specifics of the API of this particular library. Again, I love this library and I can talk about it a lot, but these things will be slightly different in other libraries. They will all have some way to get the stabilizer tableau, some way to get the corresponding destabilizer tableau. In this particular library, stabilizer view extracts this part, and more importantly, why is it called view? Because you can modify something in stabilizer view. For instance, say the first term, and let's make it equal to z. And let's print ds again, and we modify ds. ds is now completely broken. This is not a valid destabilizer tableau, but point is, with these view methods, you can get a part of the tableau and just work on that part. For convenience, for writing other algorithms, these are just various ways to extract a subset of the tableau. This library happens to have this API, inspired by APIs seen in some other places. And there's also destabilizer view, which if it acts on DS, it gives you the destabilizer part of the destabilizer-stabilizer pair. Other questions? Well, then we can go to bed 12 minutes early, and tomorrow at 9 a.m. we're starting with tensor networks.
When I look at it, then it is not.
Sorry.
We can talk about this library for a minute.
Yeah, I guess we won't have time for that. But yeah, I'll check with the other instructors and we'll try to squeeze something into it.
So I'd first check to see if it can.
Yes, this question might be done. Yeah, I did